Okay. Please, I'm not going to come and start trying to define and whatever. I want us to just know what radioactivity is, all the shortcuts, all the formulas, then we go home. Whenever I'm treating radioactivity with my students, I normally use what I call APC. Vein. Yes. Yes. So this N stands for nature. This one stands for ionization, energy. This one stands for velocity. This one stands for charge. Charge. This one stands for penetrating power. This one stands for absorption. All right. So first of all, we know that radioactivity has to do with the emission of particles, so it's in the radiation. Is it not with the release of energy, and that energy is always large. It's always large amount of energy. So when we are talking about this radioactivity, the radiation that is emitted, there are so many of them, even positron, name it. Even we have even negatron, we have so many of it, but they are just three that everybody is familiar with, which is alpha, beta, and gamma. So this thing you see right here is for us now talking about alpha particles, beta particles, and gamma particles. So when I'm talking about alpha particles, we say that it can be easily absorbed by tin foil. Yes, it can easily be absorbed. It's a calculation I want to know. You want to see what you do for me? See what you do for me? Don't worry, see, even me, I want to do calculation. See what you do for me. Under these topics now, you will go and find out all the things that concerns alpha, beta, and gamma using this. So that's your assignment. So that it will even save me time. Yes. So please, you are going home, you are finding out everything about alpha particle under this, everything about beta particle under this, and everything about this under this. Yes, that's ABC for you. Alright, please. For the calculation aspect of this, I'm looking at time. And thank God for him. Yes. So the calculation aspect of this is that whenever you are calculating radioactivity, you are expected to find what we call half-life. Yes. You are expected to find what we call half-life. Or you are expected to find out how much of the, like how much or in quantity that is remaining. So half-life is simply talking about the time for a particular radioactive material to decay to half of its quantity. So in radioactivity, it's either you are finding the half-life, which is given by T half, or you are finding how much is remaining, which is given by N, or in some textbook you see it as A, whichever one you prefer to use. But for the fact that we are going to be doing what we call chemical kinetics next semester, in second semester I will be teaching you what we call chemical kinetics. I will use A. Yes. So the first formula I want you to note under this is what we call A, the how much that is remaining, is equals to the initial amount, which is AO, initial amount, then times half, raised to power T, that is time gone by, all over, time for half-life. A stands for amount remaining, AO stands for initial amount, then times half, raised to time gone by. This T stands for time gone by. Time gone by. And this one stands for the half, or yes, for the half-life. So the H stands for half-life, the time for half-life. So you need to note this. Now another thing under this radioactivity, whatever is calculation for radioactivity that you need to know, be aware of. This equation you are seeing here comes from what we call chemical kinetics. We do it in second semester. Now another thing you need to note once they are asking you for radioactivity calculations is the relationship between half-life and decay constants. The relationship. So notice this one is when you're finding half-life. From here you can make half-life so the formula ahead. When you're finding how much remaining, notice that this is how much remaining. So I can take it that this equation is for when I'm finding how much remaining. That is 0.1 for the calculation. 0.1, you will see it. Now the second thing is the relationship between half-life and decay constant. And that relationship is simply given by T half is equals to ln 2 all over decay constant. Now watch for me ln 2. What do you have? 6 times 3, Chevy. All these things you see us doing now are things we will now do more in second semester. But in first semester you will do radioactivity. You see questions on it. But in second semester, we will do a full course called chemical kinetics. Yes, which one? T half, T1 over 2, yes. So this is the relationship, or when they tell you find half-life, this is the relationship between, relationship between half-life and decay constants. So we'll take questions on this so that we'll understand it better. So you can say where T half is equals to half-life or time to get to half of the quantity, initial quantity. Now this lambda is what we know as decay constant. If you say I'm rushing this thing, try and be fast. You know I'm rushing. You people have formed the habit of once it's 4, you want to go home.
So I don't understand.
You're not paying attention enough then. Because there's nothing to understand in what we are doing. It's just the questions I'm giving you. We've not even solved. So there's nothing to understand in what we are doing. It's just the questions I'm giving you. That when I'm talking about radioactivity, I know that radioactivity is the spontaneous disintegration or emission of spontaneous disintegration or breaking down of unstable atomic nuclei, or you say atomic nucleus, with the release of energy. So, and this release of energy also comes with emission of radiations. And under that, we have 10 popular ones, which is alpha, beta, and gamma. And I said that using this, all the characteristics of these radiations can be done under this APC vein. So once you get to do this one for me, you know that definitely this one has the highest penetrating power. This one has the lowest. This one has the charge of +2. This one has -1. This one has no charge. Velocity. This one has like 20% of the speed of light. This one has about 5% of speed of light. This one is almost the same thing as speed of light. If you check it, ionization energy. If your mass is more, you will have more ionization energy, which means that this one has more ionization energy, followed by this one. This one has the least ionization energy. In nature, this one exists as a helium particle. This one exists, helium, that is formed, and this one exists as an electron. Shall why this one exists as an electromagnetic wave? Yeah, so when you do this, you will see all the nodes to it. So there's nothing there to understand. You are the one doing the assignment. Then when I say that the calculation aspect, that when it's half-life, that we are checking two things for the radioactivity calculations. When they're asking us for half-life or how much that is remaining, and the how much remaining, this is the question we use. And when it's half-life, they're asking us, we are not checking the relationship between half-life and decay constant, which is what we have here. That's it, nothing more to it. So we can solve the calculations. So the only reason why it looks as if this radioactivity is that long is because of the fact that some of you spend much time trying to cram this thing ahead, which you don't have to cram. Okay, so please, question 1. Can I claim? Yes. But question 1. Question 1. Let me quickly post it to the group. Are like estimates of ones that have happened before. So, but you are not giving for certain or for sure that this is what it is at that particular moment. So we say it's a random process. Another thing you need to also go and read under this is who is the father of Henry Becquerel, yes. And what year? Then there's another woman that won Nobel Prize, Maria Curie, and you know she's the first woman to win Nobel Prize. No. She is, yes. And she's from Poland. That is why she's the one that discovered polonium. The element she discovered is what you call polonium. She named it after her country. And during the World War, she became very famous because she was able to use that radioactive elements to treat people. At a point, they used to normally use, even when you get to all these brushing, toothpaste and the rest, they will put radioactive materials there. But at some point, they now found out that it has side effects. Like that woman, Maria Curie, she spent so much time with that radioactivity. Anywhere she's going, she's happy. First Nobel Prize winner, woman. So anywhere she's going, she's carrying it. But towards the end of her life, it was discovered that that thing gave her health issues, serious health challenges. So go and study about Maria Curie and the husband, I think Perez. Yes. So go and study about Maria Curie. And then you also need to go and study how the investigation was made. This radioactivity we're talking about was discovered by mistake. Hope you know. Yes. That time X-rays came out newly. So this particular man was fascinated with the colors that X-rays showed. Like all those colors when it appears, all those things, he was fascinated with it. So when he was doing his own, I think that story is with uranium. So after doing his own experiment, he now kept it and then used pepper to cover it and put inside his drawer. Then when he came the following day, he noticed that there are some form of radiation from that uranium on the pepper. So when he followed it up, that is what we now call today radioactivity. So you can do research on the discovery of radioactivity. People that played the role. This Maria Curie, she actually played the role in this or got into radioactivity when she was doing her master's specimen, something like that. So go and browse all these things. You will see some points on these in your objective questions. So you need to read all about the discovery of radioactivity. Now read the questions that we have here. Somebody says, check it out, that's how we solve. We finish it tomorrow. But the half-life of air,
It looks like it's given by 48 hours.
It's given by 48 hours.
Determine the decay constant.
Determine the decay, that is longer now. Okay, so the half-life is given by 48 hours. Determine the decay constant. But let's check something. We can actually use hours, we can actually use minutes, we can actually use seconds. Should we know? Yes. But if we want to do 48 hours to seconds, what do we do?
Divide by minutes.
Is it true? Seconds, so first of all, 1 second is equal to 1 minute. Is it not true?
Yes.
60 seconds.
Watch now. 1 minute is what is equal to 60 seconds.
60 seconds.
Sorry. Maybe in the next slide. 60 seconds equals 1 minute. Now 1 minute is equal to what? 60 minutes, sorry.
Wow. 1 hour.
1 hour. Thank you very much. Let's check something. And we now know that if that is the case, this 60 times 60, which is 3,000 seconds, is equals to 1 hour. Is it not true? Okay, so let's do that our approach. We don't ever need to guess how to convert anything. Just once you're able to bring this one, put hour in the place hour, we cancel hour. So 48 hour times 3,600 seconds divided by 1 hour. You don't have to stress yourself. Just once it's conversion, they are asking you, may first. Carry the hour, be looking for where it will cancel out. So you don't know whether you're dividing or canceling. So we are multiplying. We are multiplying 48 by 800. 800. Okay. That means if you want to convert this to seconds, this is what it will be. Why I'm doing it is if you want to convert a whole, me, I will not convert my own.
Why?
You go convert it.
Reason being that if they wanted me to put it in seconds, the question could have been indicated in per seconds. You understand? But if you are really prepared enough, well, let's use seconds so that
we use both of them.
And let's say because of the fact that the SI unit of time is seconds, so let's use seconds. But you know that it's not every time they expect you to have your answer in seconds. But let's just see. So if I'm doing that, I will now have that. Putting things in order, I will now have that. See how I'm using that relationship between half-life and decay constant. 0.693 or you say with 2 all over the decay constant. Is it not true?
Yes.
Now, just multiply so that I will now have that this is going to be lambda equals to 0.693 all over t half. So if I do it, I'm not going to have that lambda is equals to 0.693 all over 172,800 in seconds. Punch for me. Lambda is equals to 750.4. Six. Okay. If, for example, I punch this thing, I don't see my answer. That means they use hour. Is it not true?
Yeah.
So you have to be very conscious because somebody might finish using this principle. Who's there? That's why it's not happening. It's also when I go to part of the book that I write E, 1 point. Then after that, I put brackets. So this is the correct one. So that one is CBT. That's why they removed all those things. So once you do this and you see that it's not safe, but I will advise you, if it's an hour, use hour. Because I'm using my experience and I've noticed that they're always paying attention to the function of this decay constant. So if you're giving hour, it means that your decay constant is a function of per hour. So if you're giving seconds, it means that your decay constant is a function of per seconds. If you are giving weeks, it means that your decay constant is a function of per weeks. Per weeks. So that's why, if you really want to solve this, before converting to seconds, I know naturally we are used to converting to seconds, but once it's radioactivity, remember that this thing is real life something we're talking about. So that your decay constant, be checking what it is so that you can be able to put it in per hour or per second or per weeks. So this one that we've done is simply putting this thing in per seconds. So that's what we've done here. So if your answer there is not in per second, you now go and divide by 48. So that you finish, you put your answer to be in per hour. Very simple. Okay, now the next question, so that we'll go. For us.
Divide that 172,800.
This one? Yes. This one over 2. This thing that need for data mean the symbol or symbol. This thing is talking about, instead of calling it time, that is T for full time. T for half time, that is half life. That's what this thing means. So anywhere you talk about half life, if you don't write it as an English word, you just say T half. That is time to get to half of that mass. Yes. Alright, so read the second question so that we can go. Okay, it's 3.5 years, Shebi?
Yes.
Now they said the average of radioactive isotope is 3.5 years. What again? Okay, they're asking us to determine decay constant. Okay, in per weeks. Wow, okay. In per weeks. Okay, yes, thank God. What we now do is to check how many weeks make 1 year. 52 weeks. Are you sure?
Yeah.
How did you get 52 weeks? 2 weeks.
It's for leap year.
Okay, that means we are going there with crammed work. Because that's what this means. Because we need to know how we are getting out. I know 4 weeks. Never happened, Shebi. Okay, but we are not putting the fact that we need edges. It's unless that. Okay, let's go with it now. So which means 52 weeks is equal to 1 year. Okay, that means 3.5 years. 182. Equals to X with Shebi?
Yeah.
Okay, so when you cross multiply, you are having what? 3.5 times 52. 182. So that means that X weeks times 1 is equal to 3.5 times 52, which is 182 weeks. Okay. But notice, remember that this one is year.
Then you can say.
Okay, then I want to, but you understand it, Shelly?
Yes.
Let's just leave it at this. So I now have this 182 with 1, and let me go back to my relationship, which is T half equals to 0.693 all over the gave us that. If you cross multiply, you now have that lambda is equals to 0.693 all over 182. Should be?
Times 3.8 times 10
So you have 3.
0.8 times 10 is
So times 10 is minus 3. Okay. And you know that this gave us that is going to, because this is a value. That is, it's just 1 over. And you know that the only thing here is weeks. So, weeks, that is week. So, weeks, yes. So that's my answer. So the last one.
The game constant. The SI is the weeks of the game constant.
You see which one? This one.
As you are collecting weeks now for lambda.
It's per weeks now.
Yeah.
See, you need to know that your lambda is a function of whatever you are given here. It's a function of it. So it's a function of your time. And notice that your time is always going under. This is your half-life. So it's decaying as a function of your half-life. So that's why we always put in per whatever our time is. I just praise somebody's learning. I hope you are learning. There are some people that from secondary school, once it's chemistry, it's not for them. Yes. So there is something we've discovered that we're going to be doing. We are going to be trying our best to say that every Saturday we revisit our past questions. So just like next week that we said we're starting marathon, we're going to be going through our chemistry past questions as well. This period is serious past question class. Because of the fact that we believe that there's a strategy we'll be using, and we have to continue using it. So this particular week that we are getting into now, everything chemistry, past question, everything is about maths, past question, biology, past question, parasitology, past question. By the time we are able to finish our past question within 2 weeks, we should be able to finish it within 2 weeks, hope you know. Yes. Because we're not going to be writing anything again. Or maybe coming to explain things. Rather, as we are solving questions, we'll make sure you get it. Whatever question that is like this is formula to go about it. So try your best to see that you're always in class next week. Give me the last question. Do beyond 262. Do beyond.
How long will you wait?
Okay, how long?
Will you wait? To see 500 grams.
To see 500 grams,
You get just 1 gram.
we get just 1. Okay, 500. How long? Okay, yeah, now try it out. Okay? Then they're not asking us that 500 grams, that is 8O. 500 grams. Yes, Nisha. That is to what? To 1 gram, Shebi? So remember that A stands for mass remaining.
Yes.
A stands for mass. T that you see here means for time gone by. Yeah. Or you call it how long. Why this one stands for your half-life. So comparing it to that our equation, we're not going to be having A is equals to A over 2 raised to power T over H. Notice that the reason why I'm using H here is that I don't want to come and write maybe T, then come and write T half again. That's why we did it that way. So let's impute everything. So now I have 1 gram. Then equals to 500 gram. I did not put my gram in kg because in chemistry I use gram. We use gram. So then half. Then I now have T that I don't know. Then all over H, T half that I know, which is what? 34. Notice that everything here is 34. So what you just do for me now is to say, first of all, half is the same as 0.5. 0.5. Then I have 500 equals to 1 gram. Okay, all raised to power T over 34. But do for me. I want you to do for me. First of all, hope you know that this thing, I cannot multiply this. Because it's at the power. Is it not the?
Yes.
So what I can actually do is to say, let me make this one to be on this own. So let me remove the coefficient. This thing becomes a coefficient. This is where most students make mistake because once you see this thing, what some people are looking for is by all means be solving. That's what some people are looking for inside the exam hall. By all means, let me be solving. Once they're pause, they will go at their hand. That's it. So at this point, you need to notice that I don't want to do anything here. So I'm seeing this thing now as a coefficient because this one is having 4. So divide both sides by 500. Very important to be remembering all these things I'm saying. So divided by 500. So let's to leave that man in the room. And now if I divide, let me just look this now because divide by 500. Divide by 500. You notice that this one will cancel out this. So yes, so I can do this. So 1 divided by 500 is what?
2 times 10 is
0.0 like this?
Yes.
Okay, 1 divided by 5 equals to
0.5.
C raised by 34. Is it what you have?
Yes.
But notice something. I cannot say go here and do square root because of the fact that it's division. Is it not true?
Yes.
So anytime I'm in this condition, I can introduce logarithm. I can introduce logarithm to both sides. Yes, I can use logarithm to both sides. I can say take the log of this, take the log of this. So that by the time I do that, okay, you've not learned that one. Then if I introduce this becomes log 0.02 is equals to log 0.5 raised power t over 34. Notice that I am now having that power because it's up here. This thing can now come down. That's law of logarithm. So that this time becomes c over 34 log 0.5. If you like, don't go and read your logarithm well. The only time you remember logarithm is when you are doing, you don't do this one, it's sweetening you. You need to be knowing certain cases like this. Once you have certain cases like this, you are thinking of it immediately. So there are certain things that even on my own, I've put it in, to myself that once I'm solving, I'm stuck with a situation whereby it's not easy for me to cross the square root over to the other side. I just say take log of this side immediately without thinking. So if I know that, I'll now have, do for me log 0.02. See what I mean? See what I mean? For those of you looking at this, assuming I have this thing to let's say this way. And I can just say cross the quality sign and take the square root. Now, is it not? But so now do for me is log 0.02 is what?
Minus
2.698. Is it what you have?
9.
Okay, equals to c over 34. But do for me log 0.5. Another minus 4. Minus 0.6. Okay. Somehow I'm solving my issues now. So I now have 0.3c. And is that minus should be? Over 34. You know this one can work because I've removed that logarithm. I have gotten what I'm looking for. Then I now have minus 2.698. See that? Minus is here, minus is here. I can cancel this minus. Are you following this class? Yes. Are you sure? But you're not writing. I'm just seeing your eye like someone that wants to cry. Okay. So I now have this, which means that anything on this one is over 1 should be? This thing can come over here. This one goes. So I now have 34, 2.698 should be? Is equal to 0.3c. What point for me? Eh?
1.7.
732 is equals to 0.3 C. Divide by side. So T is what? 305.77 because this one cancels this one. So I now have equals to T. So my T is equals, I know it's going to be in seconds.
Yeah.
So T is approximately in 3.306 306 seconds. So approximately 306 seconds. So please, when you get home today and this weekend, you will see videos I will upload on Radioactivity, questions. The same thing with our physics class. Take your time to go through it. And when we started class this session, for every day of tutorial, I normally say something about go and watch video on indices. It's important. Go and watch my video on indices. Highly important. Let us pray. Let us pray.